Start the recording. Okay, so welcome everyone to this the afternoon session today. So now we're going to have David Poland from Yale, who is going to tell us about recent applications of the numerical bootstrap.
All right, thank you very much, Miguel. It's a great pleasure to be joining you. So my goal for today was to sort of try to follow up on Alessandro Vicchi's nice lectures and show you some of the more modern applications of the numerical bootstrap tools that you've been hearing about. And along the way, hopefully I can give you a sense of, what are some of the modern techniques, algorithms, software tools that are being employed in order to tackle sort of large-scale bootstrap problems. So I'll try to give you at least some sense of the lay of the land. All right, so as you've heard, the idea behind the conformal bootstrap is to use conformal symmetry, SOD, 2 or SOD plus 1, 1, depending on which signature you're in, crossing symmetry and unitarity or reflection positivity to try to map out and solve conformal field theories. And this can be phrased in the language of 4-point functions. So you take a 4-point correlation function, expand it in the operator product expansion in multiple channels, and this gives you some kind of sum rule, which tells you that a sum over conformal blocks in one channel has to equal a sum over conformal blocks in another channel. Of course, the more 4-point functions you consider, the more sum rules you can get, and you can try to take advantage of all of them. Okay, so, and of course, key elements into these bootstrap equations are the conformal blocks, which are special functions that we have to compute in terms of the cross ratios. And the unknowns in these equations are the set of scaling dimensions and OPE coefficients. So as I think you heard previously, there's a numerical approach you can adopt to study these equations, where you ask, okay, when is it possible to sum up a bunch of functions, or you can think of them as being like vectors. When can you sum up a bunch of vectors and end up with 0? And you can do it if you're in a situation like the left, where all the vectors are sort of pointing in random directions, but you can't do it if you're in a situation like the right, where all the vectors point to one side of some kind of separating plane. And so the idea behind the numerical bootstrap is to make some assumption about the spectrum of scaling dimensions and OPE coefficients, and then search for this kind of separating plane, or equivalently search for a functional, which you can apply to the crossing relations, where in practice we take linear combinations of derivatives of the crossing relations with respect to the cross ratios at the crossing symmetric point. And this is, and we look for linear combinations of those derivatives that imply some kind of contradiction, like 0 equals a sum over positive quantities. And in practice, we have to truncate this sum over derivatives up to some order, capital lambda. And we can search for these functionals numerically by solving some kind of convex optimization problems, which are, for the most part, currently phrased in terms of what are called semi-definite programs. And these can be solved using interior point algorithms for solving semi-definite programs, and one such algorithm is implemented in the piece of software called SDPB, which is freely available. So okay, so that's the basic idea. And now one thing I wanted to mention is that in the last year or two, there have been sort of several other advances in the numerical bootstrap, which have been designed to help tackle larger scale bootstrap problems with larger systems of crossing relations. So let me just mention a few of them. So one of them is that SDPB is being actively developed. in particular with the help of Walter Landry, who's been working with David Simmons-Duffin to make an improved piece of software. And there's sort of the most recent version of SDPB is quite fast. It's highly parallelizable. It's been optimized in a variety of different ways. And so this faster piece of software for solving semi-definite programs, in particular semi-definite programs at arbitrary or high precision, has been very useful for tackling large-scale bootstrap problems. Another advance is the introduction of what's called a cutting surface algorithm, which allows you to sort of more efficiently map out the allowed region in sort of large parameter spaces. In particular, it's useful for searching for large spaces of OPE coefficients, like three-dimensional spaces of OPE coefficients, and you're trying to find some allowed point in this three-dimensional region. I'll explain explain how this works more later, but this is called the cutting surface algorithm. Another development has been something called a Tiptop algorithm, which is designed to help maximize some scaling dimension over a multi-dimensional allowed region or multi-dimensional island. And finally, let me mention a new piece of software called Blocks 3D, which has been designed for efficient computation of arbitrary conformal blocks in 3 dimensions, in particular conformal blocks involving 4-point functions of operators with spin. And so this is useful for exploring bootstrap problems involving external fermions, external currents, external stress tensors, and so on. Okay, so these are some more recent developments. Many of the software tools which sort of go beyond the basic SDPB setup are being collected in a GitLab repository, the Bootstrap collaboration repository. And so if you go there, you can see a collection of software tools, some of which are still works in progress, but some of which are quite well developed. And I'll mention a few of these as I go through my talk. Okay, so let's go just look at some of the applications of the Bootstrap. So as Alessandro described, if you just look at a 4-point function of a scalar operator sigma in a 3-dimensional conformal field theory, you can use these Bootstrap methods to place a bound on the scaling dimension of epsilon, which is defined as the leading non-identity scalar operator appearing in the sigma sigma OPE. And this bound has some interesting structure to it. It starts at the free theory value 1/2 1, goes up to some kind of kink, which appears to coincide with the known scaling dimensions in the 3-dimensional Ising model, and then goes off to the right. So this was sort of the starting point for the Bootstrap applied to 3-dimensional CFTs, and it's a very intriguing one. Now the question is, can you go further, and can you take advantage of this fact that the 3-dimensional Ising model seems to sit at a kink, and find a way to further isolate it, maybe make some more rigorous predictions for the scaling dimensions of this model. And the way to do this is to go to a larger system of crossing relations. So in particular, if you go to the crossing relations involving both sigma and epsilon, here we're also assuming a Z2 symmetry where sigma is odd and epsilon is even. And if you then further assume that sigma and epsilon are the only relevant operators appearing in the theory, namely all other operators start at dimension 3 or higher, then what happens is this kink gets isolated into some island, which is around the scaling dimension of the Ising model. And that island is disconnected from some other bulk region, which appears further off to the right. Okay, so one strategy is to look at the 5. You can look at the 5 crossing relations from the correlators involving sigma and epsilon, impose the sort of experimental fact that sigma, there are only two relevant operators in the Ising model, and then see how far you can push the numerics. Namely, we can push the derivative order to be very high and see how much the island shrinks. Actually, there's one other thing that's very useful to do in order to shrink this island, which is to do something called an OPE scan. So, if you look at the contributions of sigma and epsilon in these crossing relations, they always come along with the OPE coefficients, like the sigma sigma epsilon OPE coefficient and the epsilon 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 OPE coefficient. Okay, a priori these are unknown. So it turns out that one thing that's very useful to do is to actually input some value for the relative value of these OPE coefficients. Let me call the ratio R, which is lambda epsilon 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 divided by lambda sigma sigma epsilon. You input this relative value, and then you can check if a given point in the three-dimensional space, delta sigma, delta epsilon, R is allowed or not. And then you can search through this three-dimensional space and map out this three-dimensional space, and this gives rise to a three-dimensional island. Now, what's the point of doing this? The point of doing this is that when you input some specific value for this ratio of OPE coefficients, what you're essentially doing is excluding the possibility of having multiple degenerate exchanged operators which appear at the same exchanged scaling dimensions, delta sigma and delta epsilon, but with different values for the OPE coefficients. So a priori, that could be a possibility allowed by the system of Bootstrap equations. But if you input a specific value, then you exclude a large class of degenerate solutions. So this actually cuts down, if you project this three-dimensional island into a two-dimensional delta sigma, delta epsilon plane, you get a smaller two-dimensional projection than if you hadn't done this OPE scan at all. So I wanted to mention that's one thing that's very useful to do in order to shrink the island more. This helps get you another order of magnitude. Okay, when you apply this OPE scan technique and you push this system of 5 Bootstrap equations as far as you can, at least using 2016 technology, which pushed it to lambda equals 43, which corresponds to 253 derivatives. And if you combine that with 5 crossing relations, that's a little over 1,000 or 1,200 components in the functional. Then we managed to compute this island, which is for the Ising model, which is better than Monte Carlo by 1 to 2 orders of magnitude. And so, yeah, just to emphasize, when we do this in practice, we compute the three-dimensional allowed region corresponding to this OPE scan. This plot shows the two-dimensional projection of that allowed region. And then everywhere inside of that three-dimensional island, we can further use the Bootstrap logic to place upper bounds and lower bounds on the magnitude of the sigma sigma epsilon OPE coefficient. And then that gives the results that are shown here.
Sorry, a small question.
Yeah.
So if you look at the operators with higher dimensions, do you also have estimates for their dimensions and OP coefficients, although with maybe lower precision?
Yes. So yeah. So there are two things you can do. One thing you can do. So one of them is sort of a rigorous approach, and one of them is a less rigorous approach. The rigorous approach would be to go move around in this island, and then set up another Bootstrap problem to place bounds on scaling dimensions of higher dimensional operators. And you can make various assumptions. You could try to isolate them by imposing a gap above a higher dimensional operator and then see what kind of window it lies in. That's very computationally intensive, but it's an approach that can be pursued. Another approach, which I was going to mention more later, is called the extremal functional or extremal spectrum approach, where if you go to a boundary of the allowed region, then you can extract from the functional itself a spectrum of a solution to the crossing equations, which corresponds to the solution right on the boundary of the allowed region. And from looking at these extremal spectra, you can extract a whole big spectrum of all the higher dimensional operators along with their OPE coefficients. And by sort of moving around on the boundary, you can see how much those operators vary. And that gives you some estimate for how well you've determined them. It's not a rigorous approach because there are also some solutions in the interior of the allowed region, and you're not quite probing those, but it can give you a very clear picture of the higher dimensional spectrum. So I'll mention more about this extremal spectrum approach later, but that's one of the best ways we have to probe it.
I also have a question. So so this computation was done with like SDPB1.
Yeah.
Suppose that you repeat it with SDPB2, would you expect to be able to improve precision?
Yeah, I think I think you could push it further. I probably, for this computation, it would be straightforward to push it to lambda equals 60 or something.
So maybe some younger people should do it, like somebody who. I understand that for someone who has already done it, maybe it's not such a big challenge, but for some younger people looking for interesting things to do, it sounds like.
Yeah, absolutely. This could be improved. I mean, the other frontier for the Ising model is to go to a larger system of correlators beyond sigma and epsilon. So you could include, the epsilon prime. You could include sigma prime. You could include other operators of spin, like the stress energy tensor. So these are all different directions that can be pushed on, which might be, more efficient, ultimately more efficient ways to shrink the allowed region further than keep pushing to higher derivative order. So those are two things. I'm sure derivative order can be improved beyond this 2016 technology. And then we can also now probe larger systems of correlators.
But then since this comes up, maybe you could say, is there any expectation of whether it would be best to include more correlation functions? So improve the 5 in this bookkeeping, or would it be better to have more derivatives, so more components just for the same number of fields?
Yeah. I think in general, we've seen, we've gotten more mileage out of including more crossing relations. The pushing derivative order, it sort of slows down. The size of the island seems to start converging to some finite size rather than continue to shrink once you push it far enough. So I think you'd get more mileage out of including more crossing relations than just pushing derivative order more and more. Okay, so maybe I should go on. So beyond the Ising model, there are of course lots of other interesting conformal field theories. So another interesting class of conformal field theories are the ON vector models in 3 dimensions. Okay, you can think of this as being a theory with an n component order parameter, or you can start from a theory of n free scalars and give it a phi I squared interaction and have it flow to a conformal fixed point in the infrared. And of course, different values of n are interesting. So the O2 model or XY model describes the superfluid transition in helium-4, and there's quite precise experimental data, which was taken aboard one of the space shuttle missions in the 90s. So this is a plot showing the heat capacity of helium-4 as you cross the transition, from which you can extract critical exponents. N equals 3 is also a very interesting value. It's the model of magnetism. So it's the O3 model or Heisenberg model. And then you can also push the ON models to large N, and they have a nice 1/n expansion that you can use to do various analytical calculations in. So yeah, so this story about the kinks, computing some kinks and turning them into islands can more or less be repeated in the ON vector model. So if you look at 4-point functions of phi I, you can expand this in tensor structures of the ON symmetry, read off a crossing relation sitting in front of each tensor structure, and then study that system of crossing relations for different values of n. Then you can place bounds on different ON representations that show up in the phi I, phi j, OPE. And so this plot's showing a bound on the leading ON singlet, delta S, as a function of delta phi. And then for different values of n, you see a bound that has a kink in it. At large values of n, like n equals 20, you can see a black, you see a bound with a kink, and there's a black plus inside of the kink. So that these black pluses are showing the large n analytical predictions, I think to order 1/n cubed. And you can see that there's very good agreement with between the locations of these kinks and the black pluses, at least for O20 and O10. And at small values of n, you can compare with various Monte Carlo simulations or experimental measurements, or computations in the epsilon expansion, depending on what the most precise thing is. And there again, you see good agreement. So this is what you get by just looking at a 4-point function of phi I. You can then go to a larger system of 4-point functions involving phi I and the singlet, ON singlet. And then if you input that phi and the singlet are the only relevant operators in the theory. Sorry, this should be delta phi prime greater than 3 and delta s prime greater than 3. You assume phi and s are the only relevant operators in their symmetry representations. Then you again find some islands. So by inputting this assumption, you can isolate the ON models. It's worth saying that the islands you get by just doing this are fairly large. You can see this O4 island is quite spread out. And so you don't quite get as much mileage just by doing this as with the Ising model, but you can still seem to isolate the theories. Here's a picture of the island for the O2 model from this phi S system of correlators, compared with Monte Carlo simulations shown in this rectangle, and the experimental measurement from helium-4 shown in this band. You can see there was some kind of taking their errors at face value. There's some kind of discrepancy between the two results. And the Bootstrap island, at least using the phi S system of correlators, couldn't quite resolve this discrepancy, at least pushing it to lambda equals 35. But here I want to show you an example of where, pushing to higher lambda, you can see that the islands were shrinking, but they're sort of doing it at a relatively slow rate. On the other hand, by including more external operators into your system, you can do much better. And so if you instead go to a system of correlators involving phi S and the leading 2-index tensor, Tij, or the leading charge 2 operator, of the O2 model, then you get much smaller islands. So, so here we're now showing the islands you get in this larger system of correlators. You see you can basically gain about an order of magnitude by going to this larger system of correlators at the same value of lambda. And so this is showing the best islands that we've computed for the O2 model. This, by the way, this is coming from a system of 22 crossing equations. And as I'll describe in a moment, it's also using this, this opescan method. Okay, so first of all, here's a zoom in of the best Bootstrap results for the O2 model, shown in this black island, compared to the best results from Monte Carlo simulations. So the smallest rectangle here is a Monte Carlo simulation from Hasenbusch from 2019. And so you can see that sort of the Bootstrap results in the Monte Carlo are you know, comparable in size, at least for the scaling dimensions of delta phi and delta s. There's sort of a beautiful compatibility between the two results. They're overlapping, and this, you know, this Bootstrap island, which is essentially rigorous, can at least rule out a big portion of the region which was allowed by the Monte Carlo simulation. But by the way, down here at the bottom, I'm showing the critical exponent alpha, which is relevant for the heat capacity as determined by the Bootstrap compared to Monte Carlo. You can see the error bars on alpha are exactly the same size between the Bootstrap and Monte Carlo. And it's sort of definitively rules out the central value reported in the analysis of the experimental data. So, okay, so that of course opens the question of what happened in the experiment. That's, I would say that's still an open question. Here's another view of the Bootstrap island for the O2 model, showing that, you know, we're looking at a system of external correlators involving phi, s, and t. So you have to input, to do a computation, you have to input delta phi, delta s, and delta t, meaning you're mapping out a three-dimensional space in scaling dimension space, three-dimensional allowed region in scaling dimension space. You know, you can see that, you know, even though the Bootstrap results are sort of comparable in size to Monte Carlo in delta s and delta phi, they're quite a bit better than the best Monte Carlo in, say, delta t, which is, I gather, a harder quantity to determine. This is also a much older result for the measurement of delta t. Okay, so as I mentioned, in order to really, you know, push this O2 island to be as small as possible, it's very helpful to do this OPE scan. So we really need to do a six-dimensional search over the three scaling dimensions, delta phi, delta s, and delta t, and the three ratios of OPE coefficients involving all of those external operators. And so we're really mapping out a six-dimensional parameter space. So that's sort of a challenging thing to do. So the left plot here is showing, you know, sort of the points we computed at the highest derivative order, lambda equals 43, in scaling dimension space. And then the right plot is showing for each of those points in scaling dimension space, we find some allowed point in OPE coefficient space, and that collection of allowed points in OPE coefficient space are shown in the right. So that this right plot then gives you an approximation to the full allowed region in OPE coefficient space. So it's worth talking for a little bit about what strategy we use to sort of map out this six-dimensional parameter space. And sort of it takes a variety of different ingredients. So, okay, so one ingredient is using the latest version of SDPB, which is much more efficient than previous versions. We're running this on high-performance computing clusters and trying to take full advantage of parallelization. So at the end of the day, this computation of the best O2 island at lambda equals 43 using this system of 22 crossing relations ended up using something like 1 million core hours on we ran it on the Exceed Comet computing cluster. So we really pushed it as far as we could. A few other sort of useful ingredients in this search are the following. So one thing is that it's very helpful to take advantage of something called hot starting, where when you solve the semi-definite program, you solve the convex optimization problem using SDPB, you can give it a starting point. You can give it an input file, which serves as the starting point for searching through for carrying out the algorithm, the interior point algorithm. And one thing you can do is, so one thing that's already built into SDPB is something called checkpointing, where you run SDPB. Every once in a while, it saves the state of the algorithm. You can use that saved state as an input file to restart the computation at some later point. And then a more interesting thing you can do is you can use a checkpoint file from one computation as the starting point for a different computation. So you can go to somewhere else in parameter space, use the checkpoint file for a different set of scaling dimensions, and that serves as a very good starting point for finding the solution of a different set of scaling dimensions.
Sorry, David, there's a question in the chat. Maybe you can comment. So,
sorry, yeah. How do I see the question?
So the question is, in comparing with Monte Carlo method, is this method faster? And how does computation time increases when the dimensionality increases?
In comparing with Monte Carlo, is the method faster? Yeah, let's see. So, compared to three-dimensional Monte Carlo studies, I think it's not necessarily faster. Sort of similar amounts of CPU hours are being thrown at these problems. One big advantage of the Bootstrap approach is that it's more rigorous. So you end up with a large region of parameter space that you can rigorously exclude, whereas in Monte Carlo you're doing some best fit and estimating error bars based on that. So but in terms of CPU hours, you can I think the latest Monte Carlo from Hausenbusch and our computations are of a similar scale. I don't remember exactly how much the Monte Carlo took. In terms of how time increases when dimension increases, so with space-time dimension, the time doesn't really increase in the Bootstrap. So the Bootstrap problems, are similar in 2 dimensions, 3 dimensions, and 4 dimensions, if that was the question that's being asked. Of course, what you get out of it varies a lot depending on the dimension, and some of the plots can converge slower with lambda at higher dimension compared to lower dimension, but at the first order, it's sort of the same amount of computation time across different space-time dimensions. So that's also one advantage of the Bootstrap approach compared to Monte Carlo, since Monte Carlo scales poorly with dimension. There's a question, are we sure the experimentals are wrong? Yeah, I think it's a question of properly estimating their error bars. Probably the experimental analysis was overly optimistic in assigning error bars. But I guess, yeah, of course you could ask, yeah, is it possible this helium-4 system is actually in some different universality class than the O2 model? I don't know of any concrete proposal for an alternate explanation, but it's an interesting question to think about. Okay, maybe I should keep going. So yeah, so this hot starting method is quite useful. Then you have to come up with a, for this O2 computation, searching through 6-dimensional parameter space, you have to, come up with an approach to searching through the space of scaling dimensions and an approach to searching through the space of OPE coefficients. So the space of scaling dimensions, there are various ways you can do it, but this is a 3-dimensional space. One approach that we found works quite well is carrying out something called a Delani triangulation search. I'll describe that in a second. And the search through OPE coefficient space, for each point in dimension space, we want to know, is there some allowed point in OPE coefficient space or not? And to determine the answer to this question, we use this cutting surface algorithm that we developed for this computation. So, okay, here's one picture of the Delani triangulation search. So the idea is that you're doing a computation in dimension space. You have some set of allowed points and some set of disallowed points, and then you have to decide which point you should test next. And so this Delani triangulation approach tells you that you take all of these points, the allowed points and disallowed points, compute their Delani triangulation. So this is a particular way of assigning triangles to this grid of points. And then roughly what you do is you then pick you look at all the triangles containing both allowed points and disallowed points, and you pick some approach to identifying the biggest one. And then you pick a point in the middle of the biggest triangle, and that's the point you test next. So there are different criteria you can use for deciding on which triangle is the biggest. You could use the area. You can look at the side lengths of the triangles. They all sort of, both of these approaches sort of work. But that's the basic idea, and this gives you some sort of concrete approach for deciding which point to pick next. And this approach works in 2-dimensional spaces as shown here, but it also works in 3-dimensional spaces and higher dimensional spaces. So it's a sort of general approach you can take to searching through a parameter space. Now for each point in dimension space, you then have to decide, is there some, so there's some allowed region in OPE coefficient space, and you're trying to find that allowed region, because the allowed region is often much, it's some small 3-dimensional allowed region, and you don't know where it is, and you're trying to find it. But one thing you can take advantage of is that each time you do a computation, you find a functional, you run STPB, you actually exclude a whole region of parameter space. So, so the region, if you like, you do a computation at one input value of the OPE coefficients, you find a functional, you can use that same functional to exclude a whole region of OPE coefficient space, which is defined by a quadratic inequality, which is, precisely the inequality you would impose when setting up the Bootstrap problem. But the idea is you can use the same functional to exclude a whole region of space. By the way, you can also use that same functional to exclude some region of scaling dimension space, but that's much more annoying since you have to recompute the conformal blocks at each point in scaling dimension space. And in practice, it seems to be a fairly small region of scaling dimension space that you exclude using this approach. So at least for this particular problem in practice, we were using the fact that each functional can exclude a whole region of OPE coefficient space. And so a picture of how it works is shown above. So we start in the upper left corner. We start with some sphere that we're trying to search through, where we know one point is so there's some sphere we're trying to search through. We pick a point to test, this blue point, and then that the functional that we find that it's ruled out, but then the functional can exclude a whole region of space, which sort of lops off a piece of the sphere, and then we pick a new point to test in the middle of the allowed region, the next blue point. That again lops off some part of the sphere, and then you keep iterating until you eventually whittle down the allowed region in OPE coefficient space to be something that's small enough such that the next point you test is finally allowed, or you find that you rule out the entire region. And in practice, at least in this O2 model example, we found that you can run this something like order 10 to 30 times, and then you'll either find an allowed point or rule out the entire region. So that's sort of how it works in practice. Okay. So here's another application of the Bootstrap, these Bootstrap techniques. So more recently, we applied these techniques to the O3 model using a similar kind of system of correlators. We used the leading O3 vector, O3 singlet, vector phi, O3 singlet S, and O3 symmetric tensor Tij. This leads to a system of 28 crossing relations. And basically, we threw the same technology at it. We use this Delani search in dimension space. We use this cunning surface algorithm in OPE coefficient space, and found the allowed region that's shown here. And you can see that sort of again, it's at least in delta phi, delta t, and delta s, it's comparable in size to the latest Monte Carlo simulations. Now, one sort of interesting physics question that we honed in on for the O3 model is the question of whether the leading 4-index tensor, phi I, phi j, phi k, phi l, symmetrized and traceless, is a relevant operator or an irrelevant operator in the O3 model. So there's sort of a long history of people trying to tackle this question that I won't get into, but most results show that the dimension of this operator is very, very close to marginality. So this is sort of an interesting question that we can now tackle with the Bootstrap. So this comes back to the question of how we can probe other operators in the spectrum beyond the ones that we throw in as external operators to the 4-point functions. So as I said, there are these two approaches. There's this extremal functional approach where you can come up with estimates of the scaling dimension of this operator. And there's also a more rigorous approach where you could move around in this island and try to place a rigorous bound on the scaling dimension of this operator. So we tried to take on this rigorous approach in our study. And in order to do that, we use this thing that I called a Tiptop search, where we want to basically move around in this 3-dimensional island and maximize the scaling dimension of this 4-index tensor. The result is that we ended up with a bound which says that the scaling dimension is less than 2.99056. So our search was very, very converged, and we can basically prove that it's relevant, but it could still be very slightly so. This is an interesting physics question because it's related to the question of whether Heisenberg magnets described by the O3 model are stable or unstable to cubic anisotropy. So if you deform, consider anisotropic deformations, which preserve the symmetry of a cubic symmetry, rather than a full O3 symmetry, then you effectively deform the theory by adding this operator to the Lagrangian, this 4-index tensor to the Lagrangian. And if it's relevant, then the theory will then flow to a different fixed point called the cubic fixed point. So our result is basically a more or less rigorous proof that a Heisenberg magnet should flow to the cubic fixed point if you deform it by some cubic anisotropy.
Can I ask a question? So you several times said like essentially rigorous. Now you say more or less rigorous. So what exactly are you referring to? Yeah,
sorry. So
What are the caveats that one should be aware of? I'm saying?
Yeah. So the caveats. So okay. So why am I making those caveats? So here, we're computing some. At the end of the day, we do the 6-dimensional search. We compute some set of allowed points in dimension space and OPE coefficient space. So this set of points are some approximation to the real allowed region. And we also have some cloud of disallowed points around them. So, and then for each of those allowed points in the 6-dimensional space, we can compute bounds on various quantities. So yeah, basically, so the point is that this is still some approximation to the allowed region, and we can come up with some method for interpolating between the allowed points and the disallowed points that we've computed, and try to estimate some error bars. Doing that involves some assumptions, like you're assuming that the region is convex. And so, so it's not completely rigorous, but it involves some very plausible assumptions.
So you mean that we can never be sure 100%, at least we did not check it, just somewhere, in the middle of nowhere, there sits some point which is accidentally consistent.
Yeah.
Okay.
Yeah, okay. Yeah, maybe, people have different standards for rigorous. So. But yeah, so anyway, so up to some very plausible assumptions, I would say it's a rigorous result.
So how sure we are all physicists, right, of some sort. So when I see a number like that, I would say most likely it's 3, because this model must be nice. So how sure are you? How many percent? How much will you bet that it's not 3?
Yeah, good. So let me. I have one more slide on this Tiptop search. So that's a really good question. So that's sort of why we designed this search, to really understand what is the maximal gap in the scaling dimension, because you compute 2.99 and you're like, maybe it's just 3, So the idea behind the Tiptop search is you basically, you pick some value of the gap, you map out some approximate island, and then you try to shrink, you compute some bounding box for the island, you shrink it by a factor of 2, and then see how much could you increase this gap in this case, in the 4-index tensor dimension, while still accommodating this smaller bounding box of the island. And then you sort of keep iterating this procedure. So you map out some approximate island at one value of the gap, you go up, you map out another island, you go up, you map out another island, and then you keep doing that until, the island, you basically find that there's no island left, and you get some, big dense cloud of disallowed points right on the tip of this allowed region. And then you feel pretty confident that, there's no tiny little spike of allowed region coming out of in between the disallowed points. So in this case, I feel quite confident that the scaling dimension of this 4-index tensor is not 3. Basically because we have this very dense cloud of x's right at the very tip of the allowed region, where it just seems completely implausible that it could extend further. Yeah, so, but yeah, more generally, you have to think about whether there's any way the allowed region could escape all the points that you've computed. But in this case, it seems like the tip of, you're computing basically the tip of some spike in this 4-dimensional space, and it looks like we've mapped it out pretty well, and there's no way it could extend up to 3.
Yeah, but looking at this picture, like I don't understand. So you have this accumulation of green points at a certain constant value, but then I don't see any points between those green points and the red points right above. There are like 2 red crosses above the tip, and then there's a lot of green points below. But why are there no points in between?
Oh, sorry. There's a whole bunch of points right above the green points.
Ah, okay. They're just
sort of hidden.
Yeah.
Yeah. So sorry, they're a bit hidden by the green points, but there's a dense cloud of X's right directly above the green points.
I see.
Sorry, question. Linnea, hi. Could there be a disconnected region above it?
Sorry, say that again.
If there could be a disconnected allowed region.
Oh, disconnected allowed region above it.
Let's say a tiny one around 3, for example.
So, so in this case, what we're assuming, all we're doing is inputting the gap in this 4-index tensor sector. So, when we have a green allowed point here, it means we've input we've said we're assuming that all 4-index tensors start at dimension 2.9905 and above. So they could have a dimension anywhere above 2.9905. So, and when we're up here, we say, if we assume all 4-index tensors are above 2.9906, then that's disallowed. So, so it's not the case that you could have, a dimension of, 3.5, and that's allowed because it's excluded by the functional sitting down, these disallowed functionals that are down here. So I in this case, I don't think so. So this is, basically because we're inputting a gap in the sector rather than isolating the operator and sort of.
Okay, is it either spike or nothing, but it can't be fully disconnected?
Yeah.
Okay, thank you.
Yep. Okay.
Sorry, David. And so X, Y, Z, they are coordinates on this log.
Yeah. Sorry. So I didn't explain that. So actually, one other thing that's useful to do is, for example, when we're mapping out our island in dimension space, it's a 3-dimensional island. It sort of has a funny elongated shape in delta phi, delta s, and delta t space. But then you can do an affine transformation to make the island roughly spherical. So X, Y, and Z are some new coordinates which make the island roughly spherical. So they're related to delta phi, delta s, and delta t using some linear equation. Okay. So as I mentioned before, another thing you can do is extract an extremal functional. So you basically go to some boundary of these allowed regions. For example, you can either go to a boundary in dimension space, or you can extremize some OPE coefficient and go to a boundary in OPE coefficient space. And then from the functional right on the boundary, you basically plot it. You apply the functional to the conformal blocks and plot it, and you see that it has some discrete set of zeros, and the locations of those zeros pick out some solution to the crossing equations that you input into the program. And you can also solve for the corresponding OPE coefficients. So this is also something we can do in practice. When you apply this technique to, say, some extremal functional in the O2 model, you get a whole scattering of operators at different spins, at different scaling dimensions. Here it's shown in terms of twist, scaling dimension minus spin. And all these bubbles are showing the locations of the operators, and the size of the bubble shows you as you go across all the different points that we computed, how often does the operator show up at that value? So the big bubbles are sort of the robust operators, and the little bubbles are the ones that only appear in one extremal spectrum, but not others. I just wanted to mention there's sort of a nice Python script, which is in this repository, which can be used to extract the extremal spectra, which uses the output of SDPB. In practice, this data is kind of interesting because it gives you, trajectories of operators as a function of spin. And those trajectories of operators can be directly compared with other sort of analytical approaches to the Bootstrap. In particular, there's one older analytical approach called the light cone Bootstrap, where you can solve for these trajectories of operators in a 1/spin expansion. Roughly, you basically, by solving the Bootstrap equations in a light cone limit, z goes to 0, you can establish that there's some accumulation point of operators which has twist approaching 2 delta sigma. Intuitively, you can think of these as what are called double twist operators, like sigma derivative sigma, some composite operators with spin. And then you can, in the light cone Bootstrap, order by order solve for their scaling dimensions in a 1/spin expansion. The more recent approach is this thing called the Lorentzian inversion formula, where you can, basically compute the trajectory of operators as an analytic function of spin in terms of a certain integral of a double discontinuity of the 4-point function, and you can approximate that double discontinuity of the 4-point function using some set of known contributions. And this gives you some analytical approximations to the spectrum as a function of spin. In practice, you can compute it in terms of a big sum of 4f3 hypergeometric functions. So this is an approach that can be pursued. I don't have time to dive into it. I think it's going to be discussed more in a talk later by Johan Henriksen. But let me just show you that if you extract sort of the leading twist spectra using the extremal functional for the O2 model points that we computed, you get these data points shown in this plot. Here I'm showing the trajectories for the even spin singlets, odd spin singlets, and charge 2 operators. And these could be compared with the analytical predictions, where you approximate this double discontinuity using some number of known contributions, like the contribution of S, T, and the O2 current and the stress tensor. So we input those contributions and compute these analytical curves, and they seem to very nicely match the trajectories of operators that you can extract using the extremal functional approach. So this is one place where there's sort of a nice convergence between the numerical methods that we have for approximating the higher spectrum and analytical methods. Okay, so in the last, if I can take a few more minutes, let me just show you a little bit about what I might call the spinning frontier, where all the studies I showed you before involve 4-point functions of operators that are scalars, operators without spin. And another sort of exciting frontier of the Bootstrap is to extend these studies to operators with spin. So there's one nice piece of new software that we developed called Blocks 3D, which can help compute conformal blocks in 3 dimensions for arbitrary external operators that spin. I mean, one of the big challenges when you have spinning operators is that there are tensor structures in the 4-point function. There are multiple tensor structures in the 3-point functions. You have to understand how to combine each 3-point structure, 2 3-point structures to produce each 4-point structure. There's sort of a concrete set of recursion relations, which take the form of a pole expansion that you can use to compute the conformal blocks for arbitrary tensor structures. So, so now we have this nice piece of software for computing those blocks in 3 dimensions. There's also 4 dimensions that's a bit different, but there's also a Mathematica package called CFTs 4D for computing spinning 4D blocks developed by Cuomo, Karateev, and Kravchuk. But I just wanted to say there's this nice piece of blocks 3D software which can now be used to sort of efficiently compute spinning conformal blocks for external fermions, external stress tensors, external currents, at least sort of the simplest cases of spinning operators that are interesting. Yeah, maybe I'll skip that for a second. So let me just mention, so there's some other interesting CFTs that you can tackle from the perspective of spinning 4-point functions. So one class is called the Grosnovo-Yukawa models, which basically look like interacting CFTs built out of n fermions, psi I, and 1 or more scalars. So the simplest Lagrangian is shown here, where you have a Yukawa coupling, sigma psi bar I psi I, plus lambda sigma to the 4th. And there are also variations of these models with multiple scalars. Various values of n are interesting physically. So, the case of n equals 8 has been employed to describe possible critical points in D-wave superconductors or graphene. In the case of n equals 4, describes models like spinless fermions on a honeycomb lattice, which can be simulated, models of gapless semiconductors. So I'm not going to dive into these applications, but they're out there. And also these models have a 1/n expansion. So there are various Bootstrap results which relate to these fermionic models. For example, if you look at 4-point functions of fermions charged under an ON symmetry, you can compute bounds on the leading 2-index tensor, sigma sub t. These bounds at large n sort of also have kinks in them, which seem to coincide with the large n expansions of the Grosnovo-Yukawa models. And at small n, they also sort of have kinks, but they're a bit more washed out. And the large n expansion also breaks down. If you go to the space of delta psi and the leading singlet, delta sigma, then and assume that this leading singlet is the only relevant singlet in the theory, then you get some sort of funny, some wave structure to the allowed region. These are all showing lower bounds at different values of n. They have some funny looking kinks in them, but it's at least plausible that these kinks are tracking the Grosnovo-Yukawa models. But it's not for certain, though there's some nice agreement between epsilon expansion estimates at small n and the tips of these structures. So what I wanted to tell you is that one new application of this blocks 3D software has been to exploring systems of correlators involving the fermion, the scalar, the leading parity odd scalar sigma, and the leading parity even scalar epsilon. And by exploring this bigger system using the latest cutting plane algorithms and blocks 3D software and so on, we've now managed to compute an island for the n equals 2 Grosnovo-Yukawa model. This island makes various assumptions of gaps in the spectrum, which are motivated by the large n estimates for the operators. And in particular, this gap in the dimension of chi, this is the leading parity odd fermion in the theory, is something that's motivated by the equation of motion, which tells you that if you build a parity odd fermion like sigma psi, then that's actually a descendant of psi, at least in the perturbative description. So anyway, so this seems to be working. This technology seems to be working for the Grosnovo-Yukawa models. And we now have an island for the case of n equals 2. It also seems to be working for n equals 4, but I don't have a nice plot on that yet. Currently, we've run this at low derivative order, lambda equals 15, and we're working to push it to higher derivative order and also explore other n. Okay, so I think let me just show you one other thing, since it was, I think, mentioned previously in this workshop. Another nice application of the Bootstrap is to the sort of what you might call the n equals 1 Grosnovo-Yukawa model, a theory with one Majorana fermion and one real scalar, where you can have a model with supersymmetry, curly n equals 1 supersymmetry in 3 dimensions. This model is sort of interesting because it has potential realizations as living on the boundaries of various topological materials. So this was proposed in work by Grover, Sheng, and Vishwanath. Yeah, just to show you, this is also a theory where we can compute a precise Bootstrap island. Here you don't actually need, the external fermions, because supersymmetry tells you that the correlation functions of the fermions are related to those of the scalars in the same supersymmetry multiplet. So if you look at the system of Bootstrap equations involving external sigma, external epsilon, where sigma and epsilon are in the same supersymmetry multiplet, then impose all the constraints of supersymmetry, then you can map out an island here it's showing the island in delta sigma and delta sigma prime space. One thing this shows you is that this supersymmetric Ising model, or n equals 1 Grosnovo-Yukawa model, it actually has 2 relevant parity odd operators in it, sigma and sigma prime. The dimension of sigma prime is like 2.885 or 886. Okay, so this is another place where we can get very precise islands. Just to show you, this is using the latest version of SDPB. This is a system of 4 crossing relations, and we were able to push it to lambda equals 59. So that's sort of gives you one example of how far the latest version of SDPB can be reasonably pushed. It might be able to push this farther on a computing cluster. Okay. Finally, there's also the frontier of exploring correlators of stress tensors and currents. We performed some older studies involving 4-point functions of stress tensors, where you can sort of map out the allowed gaps in the leading parity even scalar, that's the x-axis, and the leading parity odd scalar, that's the y-axis. And you can sort of see you get an interesting allowed region where various known theories sit on the boundaries of this region or in different corners of this region. Way up here, at the top of the point labeled scalar, is the free scalar theory. It's sort of interesting that if you want to build a parity odd operator out of a single free scalar, it takes a lot of work. You have to use a lot of derivatives. You have to use an epsilon tensor, and it's way up here at scaling dimension 11. And somehow the Bootstrap knows about that. Large n limit of the ON models are here at 2,7. Large n limit of the Grosnovo-Yukawa models are here at 2,1. So sort of the Bootstrap is sensitive to all these different limits. It's sort of interesting now to go to larger systems of mixed correlators involving stress tensors and other scalars, and see how much you can refine this space, perhaps after adding various assumptions about what kind of theory you're dealing with. And I should mention that there's also some nice studies involving 4-point functions of currents in 3 dimensions. You actually get a very similar looking plot from looking at 4-point functions of abelian currents in the dimension of parity even scalar versus parity odd scalar. One kind of cutting edge study was done by Rehorst, Trevisani, and Vicky, which looked at a mixed system involving abelian currents and scalars. And so this is a nice system to think about the O2 model in, and they managed to make a fairly precise determination of the couplings appearing in 3-point functions between two currents and a stress tensor called gamma using this system. So this is sort of has been one of the more cutting edge mixed correlator studies involving spinning operators. Okay, so that sort of should give you some sense of where the frontier of the numerical bootstrap is at. So you can ask, where do you go from here? So of course, it's interesting to try to compute islands for other interesting CFTs. Some concrete targets right now are these Grosnovo-Yukawa models. A lot of interesting variations on them, like Grosnovo-Yukawa XY, Grosnovo-Yukawa Heisenberg. These are all interesting models to study using bootstrap techniques. Another interesting target is to look at conformal windows of gauge theories like 3D QED, 4D QCD, 3D Chern-Simons theory, and so on. There's this whole zoo of super conformal theories that I didn't really talk about, but some interesting progress has been made there, and there are lots of other theories you can tackle using these large-scale bootstrap techniques that I discussed. And of course, hopefully this workshop will also produce discussions about lots of other interesting theories relevant to statistical systems. So to do this, the one frontier is to really push to larger systems of mixed correlators involving, say, spinning operators. You can explore other algorithms and develop more efficient software tools. And also a complementary thing to do is to improve our analytical understanding of the bootstrap equations. So there are these various analytical approaches like the Lorentzian inversion formula, conformal dispersion relations. These methods sort of give you insights into aspects of the spectrum that are less easy to probe using bootstrap techniques, like the large spin part of the spectrum. So I think a very interesting direction is to try to incorporate analytical insights, like the fact that we know the large spin spectrum very precisely, into improving the numerical algorithm. So that's another sort of frontier for the bootstrap. Okay, so thank you very much for listening, and I will stop there.
Okay, thanks a lot, David, for this very nice review, recent work. So we have a bit of time for questions.
Hi, I'm Francesco Paresan. I had a question on the Grosnovo-Yukawa models that you were mentioning here in the last slide.
Yeah.
So there's the one with the 1 Majorana, which has been done right here.
Yeah.
What about the others that you were mentioning, the XY with 2 Diracs, or with the Heisenberg with
yeah, those have not been studied. Those have not been studied using the bootstrap yet.
Okay, but do you know if there are some obstructions, or it's just that they didn't?
No, they're just a little, they're just a little bit more complicated than the models that have been studied. So no one has, properly set it up and thrown it into the numerics yet. But I don't think there's any obstruction. I think those are very natural targets for the bootstrap. And
yeah, I see, because they are also quite interesting for convex matter. Yeah,
that's right. Yeah.
Thank you.
Yeah, absolutely.
Thank you.
Okay, well, if there are no more questions, then I propose we thank David again for the very, very nice talk.
All right, thank you.
And I'm sure he'll
Thanks,
be around
Dave. It was very
for
clear.
discussions.